Hello and welcome to this 8th lesson in this course on metric and topological spaces. In this lesson, we're going to be looking at what are called the closure, the interior, and the boundary of a subset. And as always, in the description is the booklet for you to follow along with. It's got some of the proofs in and the exercises in. Okay, so firstly, what is the closure? So if X tau is a topological space and A is a subset of X, could be any subset, then the closure of A, denoted by CL of A, or sometimes A with a bar on it. And then we've got two different equivalent definitions of this. So our first definition is that the closure is the intersection of F's, where the F's are each closed and they contain A. So, another way of thinking about this definition is that this is the smallest closed set containing A. We know it's closed because it's the intersection of closed sets, and it's the smallest because every other closed set is contained in this intersection, and so this intersection is smaller than any of the sets they go into it, any of the individual F's. And another way of thinking about this is that a point X is in the closure if it is contained in every closed set that contains A. Now the alternative definition is that a point X is in the closure if and only if every open set U that contains X has non-empty intersection with A. So that is, A intersect U is not equal to the empty set. And note this is very similar to the definition of a limit point. The difference here is that we only require the intersection to be non-empty. Beforehand, we needed it to be non-empty and not just be X. So this is slightly more general than a limit point. Now, but we can also say that the closure is equal to the A union the limit points. So there is a strong connection here. And the equivalence of these two definitions is in the booklet. And if you were to look up different books or different notes on this, you may see one or the other given as the definition, and then the other one proved as a theorem. We've got quite a lot of examples in this video. So our first example, we're going to use the example topology on a finite set from last lesson. We're going to look at the closure of these subsets. So, quick thing to note is that both sets 1 and 2, 3, well, they're both open because they're in the topology, and closed because their complement is in the topology. So, for the first one, let's look at all the closed sets containing 2. Well, this are X and 2, 3. So we intersect those and we get 2, 3. Alternatively, we could use the second definition and look at every open set containing, let's say, 3. Well, the two open sets containing 3 are X, which intersects the singleton 2, and the set 2, 3, which intersects 2. So that means 3 is in the closure. So you could use either definition. And it would be worth, when I do these examples, trying to think of them through both definitions so you kind of see how they connect. Okay, so now I've shown you the first one. Have a go at the next two on your own, and then come back to the video. Okay, now you've had a go to find the closure of 1. Well, we'd look at all the closed sets containing 1, which are just X and 1. Intersect those and we get 1. Now for C, do the same thing, but the only closed set containing 1 and 2 is X itself. Right, our next example is for R with the standard topology. We want to find the closure of the following. Now, because this is an infinite set, every one of these subsets is going to have an infinite number of closed sets containing it. It's going to be easier to use the second definition and a little bit of intuition, to be honest, to start us off, and then we can check it using the definitions. So let's have a look at the first one, 0, 1. Well, based on the terminology, I'm expecting this to be the closed interval, 0, 1. Well, so let's check that. So we know every point between 0 and 1 must be in it. Every point inside the subset must be part of the closure. So let's check the points 0 and 1 themselves. So let's check 0, any point, or rather any interval around 0, intersects 0, 1, so the point 0 must be in the closure. We can do the same thing around 1. Any open interval around 1 intersects 0, 1, and therefore 1 is in the closure. Then similarly, we could try any other point outside of that, and you can always find an interval small enough so that it doesn't intersect 0, 1. So, as expected, the closure is just the closed interval 0, 1. Alternatively, you can think of this as we take all closed intervals containing 0, 1, keep making them smaller, and 0, 1, the closed interval 0, 1 is the smallest closed interval. So you can, again, obviously think about it in both ways. Okay, have a go at the next 3 on your own, and then I'll go through the answers. Okay, so for B, the closure is just, again, the closed interval 0, 1. Then for C, again, any interval around 1 is going to intersect 0, 1 and 1, 2. So actually the closure is the closed interval going from 0 to 2. Even though 1 in the middle is missed out of the original union, any open set around it does intersect both of them, and so it is in the closure. Then the final one, we think, so all of the individual points, 1 over n, are in the closure, but also so is the point 0. And you can see this by thinking 0 is a limit point. We've kind of already discussed how the closure includes the limit points. Or you can think that any interval around 0 will include 1 over n for a big enough n. So the closure is the set A union the point 0. Okay, we're now going to look at R with the discrete and indiscrete topologies. And recall that the discrete topology had every single subset being open and closed. And for the indiscrete topology, the only open and closed sets were the empty set and the full set R itself. So, for the first example, let's find the closure of the single point 0. In the discrete topology, it's just 0. The indiscrete topology, it's the whole set R. Now have a go with 0, 1, and then come back to the video. Okay, now you've had a go. The closure of 0, 1 in the discrete topology is 0, 1. For the indiscrete topology, it's R. Okay, I think this was probably the hardest example, and it's hard to get a picture of really what the cofinite topology looks like, but it helps to remember that all open sets are of the form R, so the total set, complement a finite number of points. Or, obviously, the empty set is open as well. So this means all closed sets are either finite or the total real line itself. So let's look at the first one, 2, 3, 4. We know 2, 3, and 4 have to be in the closure. However, let's take any point not included here. So let's take the point 5. And we want to ask, is it true that all open sets containing 5 intersect with 2, 3, 4? And the answer is no. So if we consider the set R complement 2, 3, 4, this is an open set because it's R complement a finite number of points, and this doesn't intersect 2, 3, 4, so therefore 5 is not in the closure. And this is true for any number not except for 2, 3, and 4. So therefore the closure is just 2, 3, 4. Now have a go at the others on your own and then come back to the video. Although don't worry if they're quite tricky. This is definitely the hardest example. Okay, let's have a look now at 0, 1. Well, firstly, even though this is a finite interval, it does still contain an infinite number of points. And so therefore the closure is the total real line. If we take any point, even if we remove a finite number of points from the real line, well, that set is still going to intersect 0, 1 an infinite number of times. So therefore, every single point is in the closure. And then similarly for the last one, the closure of this is just the real line. Okay, this last example is kind of a bit tangential, but it's something that comes up in lots of different areas of maths, and you've probably seen something like this before if you've taken real analysis. So given R with the standard topology, find the closure of the rationals. So if we take any point, so any number on the real axis, take any open interval containing the point x, well, this interval will always contain a rational number, and therefore the closure is the whole real line. And this is a property called dense. So a subset is called dense if the closure of it is the total space. So here you might hear in a real analysis course or something based off that the rationals are dense in the set of real numbers. All right, the next few exercises, we're going to prove some properties of the closure. Now, if you just want to copy these proofs down the first time, that's fair enough. And then when we do the interior, we'll see very similar properties and the proofs will be very, very similar. So the follow-up of these exercises will be when we look at the interior. So if we want to show the set A is closed, if and only if the closure of A is itself A. And we want to show that two sets equal, so we're going to show that the closure of A is a subset of A, and that A is a subset of the closure. Therefore the sets must be equal. So firstly, note that A is a subset of A. Every set is a subset of itself, and A is closed, because that's what we're assuming. Hence, A is in the intersection of all the closed sets containing A. That is, one of the S sub alphas which we intersect over is going to be A itself. Therefore, any point in closure, any point that's in the intersection of all of the closed sets, that's in all the closed sets containing A, well, this point must also be in A, and therefore the closure of A is in A. All right, I'm going to have a go looking at proving that A is a subset of the closure. However, if you can't see it, that's okay. It'll be a very similar proof when we do a similar theorem for the interior. Okay, so now you've had a think. Let's go through this. So, closure by definition was the intersection of every closed set that contained A. Since every set in the intersection contains A, so does the intersection itself. And in fact, this inclusion holds even if A is not closed. A is always a subset of the closure. And we've seen that in all the examples we've had. All right, we want to now prove the following properties of the closure. And again, there'll be very similar properties of the interior when we do that later. So let's have a look at the first one. So the closure of the empty set is the empty set, and the closure of X is again X. So we know that's true because both the empty set and X are closed, and we've just shown that if they're closed, they're equal to their closure. Okay. All right, let's have a look at the closure of A intersect B. Well, let's take any X in the closure of A intersect B. Any open set containing X must intersect A and B. Therefore, it must intersect both A and B on their own. If it intersects the intersection, then it intersects both A and B separately. And therefore, X is in the closure of A, because every open set containing X intersects A, and similarly for the closure of B. Okay, for the next one, we're again showing two sets equal. So we're going to show that the closure of the union is a subset of the union of the closures, and then in reverse. So I'll have a go at the first one, and then you can have a go at the second one on your own. Okay, so firstly, the closure of A union the closure of B is a closed set, and it contains A union B. We know it's a closed set because union of closed sets is closed. It's therefore included in the intersection that defines the closure of A union B. So therefore, this inclusion holds. Now, have a go at the next one on your own, and then come back to the video. Okay, now you've had a go. Firstly, we're going to take any X that's in the closure of A union the closure of B. So any open set containing X must intersect either A or B. Therefore, it must intersect the union of A and B, and therefore X is in the closure of A union B, and hence we've shown this inclusion. Okay, we're now moving on to look at the interior. So if X tau is a topological space and A is a subset of X, then the interior, which we either write as int A or A with a little circle on top, this is defined as either the interior of A is the union of all open sets which are fully contained in A. So under this definition, the interior is the largest open set contained in A. Or an alternative definition is a point X is in the interior of A if and only if there exists an open set U that contains X and U is fully contained in A. Now, the proof of the equivalence of these definitions is again in the booklet. A lot of these examples are very, very similar to when we were looking at the closure. So have a go on your own and then come back to the video and I'll go through the answers. Okay, now you've had a go. For the first one, we'll look at all open sets contained in 2. Well, the only option there is the empty set. Then for B, we look at all open sets contained in 1. Well, this is 1 and the empty set. We union those and we get 1. Now, finally, all open sets contained in that. Well, the empty set is, the set just containing 1 is, but the set containing 2 and 3 is not. So we union the empty set and 1, and so the interior is just 1. Okay, for the next example, we've got R with the standard topology. Look at the interior of the following. So again, have a think, and then come back to the video. Okay, now you've had a think. The interior of the first one, well, this first one is already an open set. So the answer is 0, 1. We consider any open set contained in that. You can just keep making it bigger until we get to 0, 1. Similarly for B, the interior is the open interval 0, 1. And for C, it's just the union of those open intervals. Unlike last time, the point 1 isn't included. If we take any open set around 1, well, it's going to contain the point 1, and that's not in the set we started with. Then this last one may be a little bit tricky, but we cannot find any open subsets. There's no intervals that we can put inside this set. You might think maybe there's one at 0 or near 0. But if you try any interval kind of around 0, again, it's not going to be a subset of this. and so the interior is empty. All right, for our next example, we have R with the discrete and indiscrete topologies. So have a think about the interior of the following, and then I'll put up the answers. Okay, now you've had a go. For the discrete topology, the interior is just 0. So again, this was an open set already. Similarly with 0, 1, it's already open. And then for the indiscrete topologies, the only open set contained in either of these is the empty set. So the interior must be that. Okay, let's find the interior of the following, this time with the cofinite topology. And again, we're going to recall that all open sets of the form R complement a finite number of points, or the empty set, and all closed sets are finite, or the whole line. Okay, so have a think and then come back to the video. All right, now you've had a think. So for the set 2, 3, 4, the interior is the empty set. There's no empty set fully contained. Sorry, no open set that's fully contained in this. Because if it's fully contained in this, the complement wouldn't be finite. Then for B, well, this we can rewrite as R complement the set 1. So this is already open, so the interior is itself. Okay, now with the standard topology, find the interior of the rational numbers. And again, this will be something you may have seen if you've studied real analysis. So we take any x in the rational, so any rational number, then we consider any tiny interval around it. This must include some irrational numbers, and therefore this interval is not fully contained in the rationals. And that's true of any open interval found, and therefore the interior is empty. Okay, the following exercises are proofs of some properties of the interior. These properties are very, very similar to some properties we saw of the closure, and the proofs follow very similar structures. So again, I'm going to leave these as an exercise and then go through the solutions after, but the proofs are very, very similar to before. Okay, our next example is to show that if A is open, then the interior of A equals A. Now the proof here is very similar to the showing that if A is closed, then it's equal to the closure, except kind of in the other way round. So have a think, look back at the previous proof if you need to, and then come back to the video and I'll go through how to prove this. Okay, so firstly we need to show that the interior of A is a subset of A. So the interior is the union of all open sets contained in A. Since every set in the union is contained in A, so is the union as a whole. And in fact, this inclusion holds even if A is not open. So the interior of a set is always contained within that set. Now for the other inclusion, we know that A is open and it contains and is contained in A, or contains A, and therefore A is one of the open sets that's included in the union. Therefore, every point in A is an element of at least one of the sets in the union, and therefore every element of A is included in the interior of A. All right, we now want to prove the following properties of the interior, and again, all of these proofs are very, very similar to similar proofs for the closure. So have a go on your own, and then come back to the video, and I'll go through them. Okay, now you've had a go. For the first one, well, both the empty set and X are open, and hence, as we've just shown, they must be equal to their interior. Okay, for the next one, we want to show that the union of the interiors is a subset of the interior of the unions. So let's take any X in the union of interiors. then take any open set containing X, which we call U. U must be fully contained in either A or B. Therefore, U is contained in the union of A and B, and X is in the interior of A union B. Okay, we now want to show that the interior of the intersection is equal to the intersection of the interiors. And because we're showing two sets equal, we're going to show one side as a subset of the other, and then in reverse. So, firstly, let's show that the interior of the intersection is a subset of the intersection of the interiors. So firstly, let's take any X in the intersection of the interiors. In the interior of the intersections. Then there exists an open set U that contains X and is fully contained in the intersection of A and B. Here we're using the second definition of the interior. Therefore, this U is fully contained in both A and in B. Therefore, X must be in the interiors of A and the interior of B separately. So therefore, it's in the intersection of both. Now, for the other inclusion, firstly note that interior of A intersect the interior of B is the intersection of open sets, and so it is again itself open. And it's open and it's contained in the intersection of A and B. Therefore, it is included in the union of open sets that defined the interior of A intersect B. And therefore, if it's part of that union, it must be a subset of the interior of the intersections. Okay, our final two exercises are to prove the following theorems about relating the closure and the interior and the complements. The proofs for these are quite similar, so I'll go through the first one, then you can have a go and I'll put up the solutions for the second one. So, to prove the first one, firstly recall that the closure of X complement A is the intersection of all the F's such that F is closed and F's contain this complement. And the interior of A is the union of all open sets that are fully contained in A. Now, from here, we can set up a one-to-one correspondence between the F's and the U's. That is, for every F, we can find a U, and vice versa. And we can do this by saying either each U is equal to X complement an F, and we can reverse that to say each F is X complement a U. Then we just use De Morgan's laws. So the intersection of F is the intersection of X complement U, and then using De Morgan's law, this is X complement the union, which is X complement the interior. You may have to quickly check that that correspondence does hold, but it does. Okay, have a go at the next one, and then come back to the video. Okay, now you've had a think, I'll put up the solution. So the first step is just that reminder. The second step is again that same correspondence. We're just going to do this the other way. Okay, the last thing we're going to see is the boundary. So the boundary of A, either written as BDRY of A or this partial symbol A. And again, this has two different definitions. So the first definition is the boundary of A is the closure complement the interior. And the second definition is the boundary of A is the intersection of the closure of A and the closure of the complement of A. So this here has an intuitive meaning, and that is the boundary of the inside of A, so the boundary of A, is the same as the boundary of the outside of A, which is maybe what you'd expect. The boundary of something is the boundary of the outside as well. And as always, Proof of the equivalence of these is in the booklet.